Hello there, and welcome to this video, which is all about the energy which is released in nuclear reactions. Now, in this video, we're going to think about a particular reaction, which is the alpha decay of bismuth 212. And if you wanted to, you could pause the video right now, go off and get a periodic table and find out the equation for that. I'm going to assume if you've done that, if you want to do that, you've pressed pause and you're ready to press play again. Here's the equation. We have bismuth 212, which has got an 83 on the bottom, and that decays to thallium and an alpha particle because it's alpha decay. Those numbers should all add up on the top and on the bottom. But no worries if you didn't do that on your own. We're not focusing so much on the numbers of this process just now. We're going to look at another number, which is the mass of these specific particles, masses of the daughter and parent nuclei. I'm just going to put them up on the screen. Now you can see there, it's a couple of kind of striking points here, lots of significant figures here, and we're expressing our masses in terms of a number u. Don't worry about that just now, we'll come on to that just now. The main thing to be aware of is that when we take the masses of these particles, we notice something interesting in decay, which is that the mass of the parent nuclei, so that would be bismuth in this case, is greater than the mass of the daughter nuclei, and that's the combined mass. So if I take the mass of thallium and add it together with the mass of alpha, I get a slightly lower number. Now, why is this a problem? Well, generally we expect masses to add up. It's a scalar quantity which adds together, and so it's a bit of a problem that mass is not always conserved here. So thankfully, we have a solution to this, and that's what we're going to talk about just now. Let's first get a bit of terminology. We have something which is called the mass defect here, and that's just this missing mass. We notice here one mass is different to the other. Okay, we've lost some mass, and we're going to call that the mass defect. And what we'll do is we're just going to calculate the mass defect for this particular decay. Now, the way I would do that is simply work out the mass on the left, which is the mass of that bismuth nucleus. And notice here there's some horrible significant figures here. It's required because, as you'll see, we've got our number of our bismuth there, which I've taken from the table, and then I've got the number for both the thallium and the alpha particle. And again, I'm keeping this U number. Don't worry about that just now. We're going to resolve that in a second. So I'd add together the mass of the thallium and the alpha, and then take that away from the bismuth mass. And you notice we get a very, very small number, 0.00666. Now, I'm always suggest to you that when you do these questions, keep 3 significant figures, perhaps even more, because those small numbers are really important for this process. So we've calculated the mass defect. We're currently not working in what we would call standard units, SI units. We need to turn this into kilograms. And we notice there that we often express our masses using this thing, the atomic mass unit, and that's called U. Now, U is a standard number, which is 1.661 times 10 to the minus 27. And it's essentially the mass of a proton or a neutron, because they have roughly the same mass. Now, what we're just going to do is we're just going to substitute that into my equation. We get a much smaller number now. 1.661 times our 0.00666 gives us 1.10 times 10 to the minus 29. Now, before we crack on, the reason that we use that U is simply because of the small numbers that are involved in these processes. The masses of nuclei are very, very small, and so sometimes it's just a bit easier for us to express them in terms of U rather than kilograms. However, for doing calculations, we need to convert. So this number U would be given to you on a data sheet. You don't need to remember it. However, you do have to use it in questions like this one. So we've calculated delta M. Now, why is that delta M important? Well, if we think back to Einstein's work on energy mass equivalence, we know that masses can be converted into energy. And that's exactly what's happened here. This missing mass has become the energy released in the nuclear reaction. And this is true not just for alpha decay, but also for beta decay, for fusion, and for fission. We always notice that there's some missing stuff. And in this case, then, we can calculate the energy released by this reaction. If you wanted to, you could take a second to pause the video and calculate that. However, I'm assuming you're happy to move on. We're obviously going to use me equal to mc squared, where our c is our speed of light, and m is going to be our delta m. It's going to be that 1.10 times 10 to the minus 29 kilograms. So what we do then is we take our incredibly small number and calculate a delta E, 1.11 times 10 to the minus 29, times that by c squared, which is a very big number, and we get, well, another small number, but not quite as small, 1 times 10 to the minus 12 joules. And why are we doing this? Well, what we're doing is we're calculating the energy released, and that energy has been given in this case to our alpha particle so that it can move in the form of kinetic energy. I'll say again, in fusion or fission, this would be the energy which is released in one of those fusion or fission reactions. And you can do the calculations and show that for fusion, that releases a lot of energy, whereas for fission, that releases a small amount of energy. So if you're in my lessons, the task is going to be to use this to calculate some more energies. I want to just lay out that process for you one more time. When we're doing calculation of energy in nuclear reactions, follow this process. You're going to firstly identify which particles are the parents and the daughters. You're then going to calculate the masses of each of them. And that is going to be in terms of U. You're then going to calculate the mass defect. And that's again going to be in U. And you're going to convert the mass defect to kilograms. Finally, you're going to calculate the energy which is released in the reaction by saying E was equal to mc squared, or sometimes delta mc squared, because it shows that as the mass defect, and that's going to calculate your energy. So with that, I think we're ready to go on. If you've got any questions, please let me know.